so, okay, this is the title of my presentation. It's about binaural processing in everyday environments. This is a very flat line on the talk, so I'll show you the practical interest in this kind of application, and later on I will talk about binaural source localization, reverberation, which is actually proven in these kind of applications, and a possible approach to solving the problem of reverberation, and I'll show you some absolutely preliminary results on this. Okay, so the main question is, can a sound source be localized with two sensors only? This is basic, the idea, the question we try to answer. Let me show you a very short movie about the fox walking also in fresh snow and looking for food. So this is basically a primary need, let's say. So I was actually very impressed when I looked at this movie for the first time. And as you saw, there was nothing on the snow, and this fox could hear noise coming from beneath the snow somewhere, and using only his or her ears could catch actually the little animal which was doing something on the snow. So. This is a real need, of course. It's a real, well, this fox was looking for food, so it's a primary need, we'll say. But also, we might have also other interests in this kind of application. So, first field could be robotics, for example. So we might think about robots. I think these are neck robots from 2005 or something. They have a number of different sensors mounted on the emitter. They also have some speech recognition microphones and some direction detection microphones. So of course, use of acoustic information is important also in robots. You might have robots trying to explore an unknown environment where maybe video information is not useful because of smoke or because of darkness, for example. Maybe because the robot's looking for a source which is hiding behind an obstacle. So in all these cases, actually, the use of all the information is actually useful. So this is first field of application. Second field could be the field of hearing aids, where we might have also like little devices which are actually mounted inside the ear. We might think also like external devices like this one. And in all these cases, we might think about, we should think about a couple of macros. We should try to replicate the audio system in a human. So this is a second field, but also we might think about video games, for example, where we might think of a player wearing these headphones, and the headphones are reproducing the effects of an environment, which actually is a virtual environment. And so in this case, we might use, might use the HR or IR, which are the head rate and impulse response of the room, to find these two impulse response of H left and H right. It could reproduce the effects that the sound would have on the listener. And this would be, okay, this application on video games, on virtual reality more general, on sonification, music composition as well. So this is actually a third field of possible application, but I'm sure we could find other fields as well. In this talk here, I'm going to talk about this specific topic, which is actually binaural source localization problem. So binaural sound source localization is the process of estimating the position of sound source using only two stationary microphones. So we know that this localization of sources happens in humans in a very complicated situations. We might talk about the cocktail party problem, so the problem where we have a number of persons speaking at the same time in a closed room. So this is a really difficult problem. So actually we wish to develop a system which would approach the flexibility and vastness of human acquisition capabilities. And this should happen with different sound sources and in the presence of vibration. So we think about room acoustics. Here I'm going to talk about this specific approach, which is based on the ILD and ITB model of the binaural hearing system in man. This approach is quite old. The first analysis of binaural perception was made by John Stutz, which is known as Lord Rayleigh, beginning of 19. In this approach, we're working on two physical cues. The first one is the interaural level difference. So the difference in the sound levels between the left and right ear. The second cue is the ITD, the interaural time difference, which is the measure of the time difference of arrival of the signal to each ear. ILD and ITD can be used to give information on the position of the listener with respect to the source with respect to the listener, of course. ILD works, well, depends on the shadowing effects of the head and torso. So in a listening scenario, contribution comes also from the shoulder, from the head, and not only from ears, so the ear canals inside, and the system inside. On the other hand, ITB is linked, depends on the direction reliable, and there is a simple geometrical relationship showing this. Actually, a single binary cue is not enough. So we cannot use only ILD or only ITD to localize a person or an audio source in an environment. So there is a way of making them to work together to perform localization. Actually, ILD gives information especially on a frequency range which is higher than 1.5 kilohertz. So when the wavelength of the source signal is small compared to the average human head. So if we consider that the mean radius of the human head is 8.75 centimeters, this gives this lower limit for the ILD. So ILD is used over 1.5 kilohertz, while actually ITD is useful only below the same threshold. This is because of maybe, for example, from aliasing. So, for example, here you have two sinusoids. If you consider this as a point of when the wave reaches the left ear, the right ear captures actually the same sound in this other instance. So if the frequency is low enough, there is no aliasing. While in this case here, the sign is too high, it's not possible to correctly detect the time instant of arrival on the other ear. So ITD is useful below actually this section. I will show later how can we use these two cues together. But for a few slides, I'm going to talk about vibration, because vibration is a typical phenomenon which is actually common to closed environments, of course. So, of course, vibration is a complex phenomenon, and usually vibration is characterized by vibration time. And the problem is that when we want to localize a source which is active inside the closed environment, the vibration can actually deteriorate our estimate. Let me show you this example. This is a sentence, thank you for tapping on the central line. This is recorded in an echoic environment, so each phoneme is actually separated from the others, while in a quiet environment, quite a reverberant environment, the evolution time is 1 second, which is pretty high. Usually we consider as a revision time, we consider a revision time of 0.25 seconds as a threshold between a low reverberant environment and a quite significant derivation in the same environment. So I guess that this 1 second is a very high measure. So you see here, the phonemes are actually mixed together. So we talked about self-masking or overlap masking that actually make, for example, localization a very difficult task in this case. So the effects of self-solid localization is to mask the directional rattle because of reflections, of course. And this effect gets worse when vibration increases, of course. Then we have the model, which actually Augusto talked about it a little bit, which is the mathematical model of vibration inside rooms. We might use this for simulation, of course. Now let me get back to the problem of binaural socialization. The possible approach was developed in a paper by Viste and others in 2010. And they showed that it's possible to combine ILD with ITD to perform localization. Well, this is possible in the absence of vibration. So, let's keep on this going. Okay, in this model, in the model that we are using, actually, the impulse responses depend on two different effects. The first effect comes from the acoustics of the room, so we should take into account the fact that localization must happen in a closed environment. So we might take into account the presence of the impulse responses of the closed environment where localization happens. The second effect is head directional filtering, and this is taken into account by using some functions, the HR, TF functions, which are actually available also on the website, on the web support if you want. Okay, the algorithm basically consists in computations of the short time Fourier transforms on the 2 ears and computation of these two functions here, which actually depends on the difference in amplitude between the two functions and the phase difference between the functions. And so these are actually the estimates of the ILD and ITD. These two functions should be compared with functions that are actually available and that are either measured on real subjects or mannequins in some cases. So these are functions that actually are available. And from the comparison between these functions and the other two functions, we can actually construct a localization procedure. This is a typical head-weighted tensor function. It's a function of the azimuth angle and the elevation angle, showing that there is a variation in both in elevation and in azimuth. So knowledge of the point on this three-dimensional curve will give the position of the source. This in an anechoic environment. Okay, how is made the localization step actually? Okay, from data from the audio that is received from these two microphones, actually we might compute the ILD and the ITD, and these two functions are computed actually these two functions are mixed together. Let me show you straight results. For example, well, in this case, okay, these are the case of source signal, actually the Gaussian noise in a room with different varying revision levels. This is all the simulations. For example, here we have the ILD computed for 0.1 duration time, and the first column refers to 0 degrees of azimuth. So this is only azimuth localization. So we think about localization where elevation is kept fixed. So the figure up here refers to this elevation in 0 degrees. But this is the 20 degrees column, this is 45, 60, and 80 degrees. So it's clear that with low elevation, the information given by ILD is quite, let's say, it's not precise, because we have here a quite large vertical column, while the information given by ITD is ambiguous because of the wrapping. We didn't talk about wrapping, but the problem is that we don't know which the wrapping factor is in this case. So we use these two information together to select the correct column in this figure here. So this is the result of combination of ILD and ITD. So in this case, with low elevation, we have a clear information on the direction of the sound. This is true for the center position, for 0 degrees, and this is probably still true for the very lateral position, for 80 degrees. But it's not true anymore for high elevation. So we tried actually elevation also higher than 0.5 seconds. But also at this, for this value elevation, the things are actually bad, they don't work actually. This is true for Gaussian noise, it's true again for speech. Let me show you the same results in a different form. Here we have, for each, okay, the first column is for Gaussian noise, the second column is for speech. We have, in this figure, we have different curves that refer to 0 seconds of elevation time, 100 milliseconds, 300 milliseconds. So this is a case of a central source. And so we see that with no reverberation we have a very low peak, meaning that localization in azimuth can happen without ambiguity. But this is true for Gaussian noise and for speech as well. But it's clear that when reverberation is even 100 milliseconds, localization is still possible for z degrees, but well, it's not possible more, for example, in this case here, which is 45 or 60 degrees Celsius, I remember. So, well, 45 and 60 and 80. So, for lateral position of source, localization is not possible more even with very low reverberation. Actually, the conclusion is that reverberation actually is problem for localization. Also, when we use ILD and ITD, we're working on this. Actually, we also obtain some results with caps for filtering, and we think about working on some other approach. Actually, we just submitted a paper on this to the journal, and so we wait for this, of course. And later on, you will be able to see a demonstration using this mannequin, actually, which is called Jackie. And so this will happen after lunch, I guess. And briefly, this is a group we're working. So I'm working with Scientifiche that are at the Italian department in Rome, Università La Sapienza, working with some other students. These are present classes, and we're making research on different topics. This is the very last slide. Thanks a lot. If you want more information, this is my address, my web address, and now I'm available for questions.